Many areas of analysis. A little bit of progress. See how far we can go. Okay. So I'm going to start here with maybe a slightly provocative definition. There are many, many definitions of amenability, some formally stronger than others, in what you might say is almost the strongest formal definition, I think, formally strongest definition. I described it here in its most powerful incarnations is as follows. Amenability, as I've described it here, an organizing principle for detecting, manipulating, and managing structural data. So one of the main goals of this talk is to explain exactly what that means, maybe from a conceptual level, and also how that plays out in examples. So amenability, it is uniquely special, I would say, as a property in analysis because of this feature. It allows you, it's a kind of finite or finite dimensional approximation principle, as I say here, that allows you to organize data. So it's a tool. On the other hand, it is a property that an object can have. In group theory, dynamics, operator algebras, we talk about immutable objects. So you can have objects that have this property, but can be studied themselves using this principle. So that I would argue this is kind of a unique situation. And this has very, very interesting consequences. One can ask many questions. So one question is, well, if this is just an organizing principle, maybe it is just purely form. Maybe there's no content to it. I mean, maybe the objects that possess this property are somehow empty, quote unquote, as objects. They don't have any content. There is a sense in which this is true in some areas, as we'll see this in von Neumann algebras. In other situations, like in group theory, this is not the case. And in C-star algebras, this is also not the case. And this has extremely interesting consequences. So you can apply this concept of amenability, for example, in C-star algebra theory, to classify. You can provide a very, very detailed fine-scale analysis and actually classify your objects in terms of combinatorial or related data. So as I say, this is the main theme, perhaps the main theme I want to drive home today is that amenability plays this double role somehow. It's a tool, it's a principle, it's also a property that an object in these various areas can possess. So I mentioned group theory. So in group theory, Fulner tilings. So tilings by approximately invariant sets. I'll give you some pictures of what that means. Correspondingly in dynamics, so actions on measure spaces, also actions on compact spaces, as we'll see a little bit later here. Tower decompositions by approximately invariant sets. Again, I'll explain what this means. In operator algebras, things, in a sense, simplify. We talk about finite dimensional approximation, and amenability is somehow, it can be expressed in different ways, but essentially it's a property of finite dimensional approximation in its strongest possible form. I could have added another item to this list. So in this morning's session, Francois's talk, the last talk, so he was talking about measured equivalence relations. So if you're familiar with all these things, that's one item that's conspicuously missing here. So equivalence relations, they do provide a bridge between operator algebras and groups and dynamics, a very important bridge. But there's actually a reason that I left it out here, perhaps unconsciously. So what I'm going to talk about today and in the applications, these are situations in which we can jump directly from one to the other, from groups and dynamics, these tiling principles in groups and dynamics, to operator algebras, to finite dimensional approximations, bypassing this equivalence relation viewpoint. But I should stress, and as we saw in Francois's talk, this is a very powerful viewpoint, which has been developed, especially in the last couple of decades, with many, many powerful consequences. And that, for many applications, that's a viewpoint one should adopt. But the idea of today's talk is to somehow bypass that and see what we can do directly by studying tilings and groups and their analogs for dynamical systems. So amenability as such, I mean, as a property, this was originally defined by von Neumann in the late 20s as a kind of response to the paradoxes of Hausdorff and Banach-Tarski. So the Hausdorff-Banach-Tarski paradox about decomposability of the sphere. In fact, you can decompose a sphere into finitely many pieces, move those rigidly to construct two copies of the sphere. So this ultimately boils down to paradoxicality phenomena inside of a free group. So it essentially, modulo some extra technical complications, reduces to a group theoretic phenomenon here. And the existence of a finitely additive probability measure on your group is an abstraction of this kind of paradoxical decomposability. So this was the original definition of von Neumann here. He named these measurable groups, messbar. And then later on, the term amenability was introduced, I believe by Day, as a kind of pun. Mean, meaning average in English, so amenable group. And nowadays, I think, usually translated, I guess, in other languages, even back into German as averageable groups, amenable groups. So equivalently, you can describe this functional analytically as the existence of an invariant state on L infinity of G. Characterization here due to Tarski that this is equivalent to the non-existence of paradoxical decompositions. I'm not going to go in this direction, so I won't tell you exactly what that means. What I'm interested here is the Fulner property. So this came a little bit later in the 50s. So this is a characterization of Fulner here in terms of the existence of approximately invariant finite subsets of the group. So the integers and z squared, for example, I've illustrated here. These are the paradigms of amenable groups. So in z squared, you can take a large square. This will be approximately invariant, proportionally speaking, under translation, say by one of the generators in z squared. So amenable groups are groups that share this property. So some examples down here, abelian groups, solvable groups, the Grigorchuk group, which you've definitely seen this week. Groups, okay, and related groups. Yes. And amenability is closed under various natural operations, taking subgroups, inductive limits, extensions, and so on. So it's a very large class of groups. This might be, well, okay, some groups will come back. One of the hallmarks of this theory, I think, and maybe another theme of my talk here is that, again, this somehow accords with my what I initially said at the beginning here. Amenability is a principle. And when you're trying to prove something about amenable groups, one should view it that way and not view it through examples. If you're trying to prove something general about amenable groups, one should forget about examples. And we'll see what I mean in a moment here. I'll give you a good illustration of that paradigm. On the other hand, the world of amenable groups is really inexhaustible, I would say. It's always somehow feeding us surprises. Even though we think we know amenability and amenable groups very well, that's very far from being the case, as we've already seen this week. But from this abstract, somehow one axiomatic viewpoint here of the definition of amenable group, for many purposes, one should not think of particular examples. One can go further here. So not only do you have this Fulner property, but you have a nice tilability property. So this is the Ornstein-Weiss tilings. I'll give you a picture of this in a moment here, that say that if you give me any epsilon, there's some integer n, depending only on epsilon, such that if you have n subsets of your group, which are approximately invariant, one with respect to the next in sequence, in this sense up there, then any much larger finite set, which is sufficiently invariant with respect to these t's itself, can almost be tiled by these TIs, epsilon quasi-tile. You have to allow a little bit of overlap, and you won't be able to fully cover this large set, but you can almost tile the large set. And this also indicates already another important principle of amenability is to play off, especially these tiling properties, at different scales. This is a very powerful tool. Sometimes one forgets about this. Sometimes one has to apply this tiling principle at 3 or 4 different scales simultaneously. This is a very important feature of this tiling phenomena, and it's already kind of built into this Ornstein-Weiss tiling principle here. Another thing I might mention here, so eventually I'm going to get to operator algebra, but we'll discuss operator algebras. So von Neumann was essentially, if you go back to the late 20s, early 30s, he was the inventor of operator algebra theory. Operator algebra is split into 2 main branches. You have the von Neumann algebras, the measure theory side, and the C-star algebras, the topology side. I will discuss both of these branches. As I mentioned, so von Neumann introduced this notion of amenability. But what's very curious here is that he never made the direct link between amenability and operator algebras. So when I say direct, I mean in terms of this Fulner property or any kind of tilability condition. He did introduce, along with Murray, his collaborator, in the series of seminal papers in the 30s and 40s on operator algebras. He did introduce this idea of finite approximation in operator algebras and develop that. We'll see a little bit of that later. But a direct link, he never saw, which is a little bit curious. On the other hand, an indirect link, he did see. He did see, and I'll also explain this a bit later. He studied, so he noticed at a certain point here, along with Murray, that if you take this idea of looking for invariant means on the group, instead of looking at left translation on the group, you look at the action of the group on itself by conjugation. Then the fact that if you have something like a free group will also have this paradoxicality with respect to conjugation, not only translation, but conjugation. And this turned out to be important for proving something novel in the sphere of operator algebras. So that is something, I'll explain that in a moment here. That is something he did point out. And this is one of the other themes, the other major theme of my talk here is that when you pass to operator algebras, really, it's a passage between looking at left translation on a group, and looking at conjugation. Conjugation and commutativity, commutation principles, commutation relations, that is what is central, that's a pun if you know operator algebras, central to the theory of operator algebras, studying commutation relations. This is an incredibly important tool, and this is how one transitions from amenability in the group theoretic world to operator algebras at the technical level. On the other hand, if you want to make some conclusive statements, amenability should translate into finite dimensional approximation. This kind of commutation, the study of conjugation and commutation relations, that should somehow disappear at the end. But the point is that you have to pass through it. And I think this is one of the reasons why it was unclear at the time of von Neumann that this is what one should do. But he already saw, so he already maybe unconsciously foresaw somehow the tool that you pass to conjugation. This is the key step in passing to operator algebras. Then one has to somehow bring it back into the world of finite dimensional approximation. This took a few decades, and it was then the work of Kahn in the 1970s. So as part of his Fields Medal citation in the 70s, that he was the one who finally established the link between this, in particular, left invariance, this invariance that we see on groups by left translation or right translation, and this idea of conjugation invariance or commutation relations in operator algebras. But this work of Kahn, it passes, so very interesting, it passes through all this conjugation business that was already incipient in the work of Murray and von Neumann.
Yeah, already with property gamma, there is this.
Property gamma, yes.
So already for Neumann.
So we will get, I won't mention, we will get to, essentially something like that. So, well, here's a picture of the Ornstein-Weiss-Fulner tiling argument. So you have a group, this is your group, an amenable group. So this is a very large Fulner set. So these dots represent elements in the group, right? And the circle is just to indicate that we've sliced out a finite subset of our group. And let's say it's approximately invariant under translation with respect to some smaller sets. So when I say Fulner set, I mean a set that's approximately invariant without specifying the tolerance. This is invariant under translation. So we want to tile this set. So we take the first of the TIs in that initial list tiling sets, and we look at all of it. We take one of those TIs, T1, and we look at all of its translates inside of the group that lie inside of this big set. So I've drawn a few of them here, but you take all of the translates. These, of course, will almost cover this whole set. The whole set is approximately invariant with respect to these smaller tiles here. But this is very far from tiling. There's too much multiplicity. There's way too much overlap. So you have to somehow disjointify this. And but this is something you can do by combinatorial argument. If you allow a little bit of overlap, which is a little bit paradoxical, you have to allow a little bit of overlap between these sets. But up to that problem, you can extract a finite collection, well, everything's finite here. You can extract a sub-collection of these translates, which are almost disjoint, and cover an epsilon proportion of this set. Epsilon. So epsilon is the parameter at the beginning. We're trying to actually cover this whole set up to within epsilon error. At the first stage here, we've only been able to cover epsilon of the whole thing. So it looks like we're almost no better than what we started with. But the point is that now you can increment this. You can take away those sets, and now you apply the second set, which so the initial set here, the bigger tiles are approximately invariant with respect to the next tiles. So the next tiles are much, much smaller. This is this idea of playing off different scales. And so you take away those initial tiles, which I've done here, And now you repeat the process as if now your set is just what remains. And you apply the same procedure now, but just using these smaller tiles. And at that stage, at the next stage, you can cover epsilon proportion, what remains, and so on and so on, and so on and so on. And this is a geometric incrementation. So after n steps, n depending only on epsilon, you will have covered all but epsilon of the space. Right? So this is, as I say, you would never come up with this argument just looking at a concrete group. And we don't know, I mean, it's an open problem whether one can actually get away with a single tile and do this, monotilability question. I mean, in most known amenable groups, we know that you can get away with a single tile in doing this. But in general, I mean, this argument works in general, and this argument, this tiling principle here, it's sufficient for proving many things and defining well, for carrying out many constructions, defining things, manipulating things. This is sufficient for a great many purposes. It's an extremely powerful tool. So here's the corresponding principle in dynamics. Instead of just looking at the group internally, you can let it act by probability measure preserving transformation. So X is a probability space here. You get a similar picture here. Okay, for the purpose of illustration, I will draw these. So this is a decomposition. This is a partition of our space, X. And each one of these towers is supposed to represent, well, there's a base, so there's some measurable set, and all of the levels, quote unquote, above the base in each one of these towers here is generated by applying elements from a Fulner set inside of your group. So the whole tower itself, these consist of measurable levels, the whole tower itself is somehow approximately invariant under applying group elements. The picture is a little bit misleading here because, I mean, this is maybe what you'd get if it was an integer action where you actually have a hierarchy. But for a general group, there's no hierarchy in these towers. It's just for the convenience of illustrating this in 2 dimensions that I do this, yeah. And so this is Rockland. So in the case of integer actions, this was known much earlier. So these are Rockland-Kakutani towers for integer actions. So this goes back to the 50s. And then the 70s, then Ornstein and Weiss discovered how to do this using this tiling argument. For single transformations, you don't need this recursive tiling argument that I said. You can do it using recurrence and so on. It's much, much simpler. So it was actually a major leap to be able to do this for amenable groups. And of course, but in the case of single transformations, one gets something, you get more information in a sense. So what's an application? So what are some examples of measure preserving actions? Classic examples, we've seen these several times this week. Bernoulli actions, where you take your group, you take some measure space Y, and you copy out the measure space over the group, take the product measure, and G acts by left translation. So these are Bernoulli actions. The construction is very simple, almost deceptively simple. It looks like there may be not much to say here, but nothing could be farther from the truth. Bernoulli actions are very, very rich class. They're still very much worthy of study. There's lots of things we don't know about Bernoulli actions. You could spend your entire career studying Bernoulli actions. But one of the most celebrated results here in ergodic theory, initially due to Ornstein for single transformations, and then Ornstein and Weiss, maybe this is one of their motivations for proving this tower decomposition here, was to extend this to all countably infinite amenable groups. It's an entropy classification of Bernoulli actions. So entropy is a numerical invariant. It turns out it's a complete invariant for Bernoulli actions of amenable groups. One can also extend this to non-amenable groups, but this is done via some, I think this was first observed by Stepan, yes? That you can apply some induction process.
No, just group contains element of infinite order and immediately
yes.
sign result.
Yeah, it's an induction argument, yes.
And now Lovis Browen and others try to prove to all groups, torsion group problems.
Right, yeah. So it is a group induction argument. I think what Lewis did was just adapt that to the equivalence relation setting, yes. So they were able to do it. So the only problem is we don't have a viable notion of entropy for all groups, but modulo that problem, we basically know this for all groups, quote unquote. I mean, the non-trivial direction by this induction procedure, we do know for all groups. Here's just a brief picture of how this, some ideas here. Going back to my claim here that amenability is an organizational principle. It's kind of like a shelving unit for distributing information, right? So if you have two Bernoulli actions here on the left and right, I'm not going to define entropy here, but the idea is that entropy is an invariance, and that two Bernoulli actions can have the same entropy without in any way looking the same. I mean, their base could even have, they could have finite base sets of different cardinality. Nevertheless, the entropy could be the same. There's an distribution or partition principle, the Shannon-McMillan-Bryman theorems, that says that if you take, well, in this case, if you take two Rockland towers here, it's a single transformation as I've illustrated here, then the statistics with which a point, I mean, so these are sequence spaces of 0, 1s or 0, 1s and 2s. The statistics with which a point, well, let's say visits the sets that are, whose membership is determined by 0, 1, or 2 at the identity, right? The somehow the statistics of the configuration of a point over finite windows, those are roughly equidistributed at a logarithmic level. And the number of columns here, the number of possible configurations determining these statistics here, that's governed by the entropy. You roughly have the same number of columns at a logarithmic scale. And then one can do a matching argument to replicate the canonical partition on this side over on the other side with a partition that models the entropy of the partition on the right side. And then the miracle is that if the actions are Bernoulli, that's the case here. I mean, this equidistribution works for all ergodic actions. But if the action is Bernoulli, then one can repeat this process and improve somehow the modeling the partition on the right by the partition that we see here on the left, determined by these 0s and 1s. And the miracle is that you can kind of bootstrap your way up to somehow via kind of Cauchy limiting operation to get an exact model on the right for the canonical partition on the left. And one can then establish an isomorphism. So this is a remarkable fact. So I hope that's kind of an illustration here of what I mean by the Rockland lemma, amenability as an organizing principle. It's interesting that the tower itself in the argument, it does introduce a little bit of entropy, but very small. So this is what I mean by amenability via Rockland towers, for example, has no content. It's pure form. It has almost zero entropy. It doesn't contribute anything. It just allows you to organize your data so that you can manipulate it combinatorially. Okay, so now let's move to von Neumann algebras. As I said at the beginning here, so the von Neumann algebras are the measure theory of operator algebra theory, if you want. We had a nice introduction, so in Younglei's talk this morning, he gave us a nice review of von Neumann algebras. So these can be described as certain star subalgebras of bounded operators on a Hilbert space, closed in an appropriate weak topology, the stronger the operator topology. The commutative von Neumann algebras, these are L infinity of X, so those are something very familiar. At the other end, extremely non-commutative von Neumann algebras, so ones which have trivial center. So the only things that commute with everything in the algebra are just the scalar multiples of the identity. These are the so-called factors. And I'm interested here in the 2-1 factors. Those are ones that in addition have a normal trace. So they have a functional that plays the role of integration. So we might think of these as non-commutative probability spaces. But this functional is actually unique, unlike on ordinary probability spaces. So that's an interesting feature here. And hyperfinite factor here, or hyperfinite 2-1 factor, if you can express it as the closure of an increasing union of finite dimensional algebras. So this is exactly what I mean here by finite dimensional approximation. So there are many ways in which you can construct a von Neumann algebra by taking inductive limits or increasing unions of finite dimensional algebras. One is to take an infinite, popular way here, take an infinite tensor product of 2x2 matrices under iteration, and then close that off. You can take a trace on each one of these, the standard trace on matrices, take the product. You can use this to build a representation and close it off. And you get a nice von Neumann algebra. And then one of the fundamental results of Murray and von Neumann here is that there's a unique one of these. Doesn't matter how you piece together these finite dimensional components, you always end up with the same thing, as long as it has a normal trace in the end. There's only one of these, and R is the canonical notation, the conventional notation for this thing. This is the hyperfinite 2-1 factor. So there's only one of these things, and this is an example of what I meant by saying that in some situations, there's no content to amenability. So here there's a unique object. It's just pure matrix. There's nothing beyond somehow pure matrix, finite dimensional matrix structure in the hyperfinite 2-1 factor. There's no possible variation to change up the global structure. You always get the same thing. Of course, that's incredibly useful for many applications. On the other hand, so what are some other ways of constructing von Neumann algebras? This also we've seen a few times, I guess, so far this week. So let's go back to actions. If you have a free ergodic measure-preserving action on a probability space, we can build a von Neumann algebra from this. We take the L-infinity functions on the space, and we enlarge it with elements UG corresponding to the group elements here, and they should satisfy this relation. So we implement the action of our group on L-infinity functions by composition. We want to replicate that or implement that by conjugation inside this von Neumann algebra. So we've simply enlarged L-infinity by throwing in elements that implement the action by conjugation. So they become inner automorphisms algebraically. And then one has to, so there's details about how to construct this, but one uses the left regular representation of the group. So acting by translation on itself under composition on L2 functions on G. And then we combine this with L-infinity to form this algebra. One can just look at the group itself. The left regular representation will generate itself some 2-1 factor. That's L of G. That's the group von Neumann algebra. This will be a factor if in the group, all of the conjugacy classes, except for the one of the identity, are infinite. That's ICC, infinite conjugacy class. So one can do this for any group, but one won't necessarily obtain a factor. But if your group has infinite conjugacy classes, which is usually the case, unless one is interested in the abelian groups, for example, but it's often the case that groups are ICC, you'll get a factor out of this. So here's the famous type decomposition. We've even seen this week of Murray and von Neumann. So they applied this to von Neumann algebras. Maybe a little bit non-descriptive as terminology, type 1, 2, and 3, but somehow it's become familiar, and I've sort of warmed to this, and I like this terminology. I think it should be used more because it really describes, despite the fact that 1, 2, and 3 doesn't describe anything. Once you understand what they mean, it really does serve as a nice shorthand for many principles in operator algebras and dynamics. So an important idea in von Neumann algebras, you have many projections. So self-adjoint idempotent. So projections, they allow you to express the notion of scale in the von Neumann algebra. So if you have a trace, you can take the trace of these projections, and that gives you a numerical, if you want, it's a quantification of the notion of scale inside of a von Neumann algebra. So if you have a von Neumann algebra and a projection, you can cut down the von Neumann algebra by the projection. So look at all elements you obtain by multiplying on the left and right by the projection. That'll give you a smaller von Neumann algebra. We can study this. And that von Neumann algebra is at a smaller scale. Somehow, and the scale then would be represented by the trace of this projection that you use to cut down. And these scales then, so the interesting thing here, in a 2-1 factor, that's under the 2-1 case, all possible values between 0 and 1 occur for the traces on projections. And the trace of a projection is completely determined by its unitary equivalence class. So two projections have the same trace if and only if you can conjugate one to the other by some unitary element. So algebraic equivalence, quote unquote, is the same thing as somehow numerical equivalence. So a very powerful principle. And somehow, if you knew this, you might suspect that maybe there wouldn't be too many 2-1 factors. I mean, at the beginning, it wasn't even clear to Murray and von Neumann that there wasn't any factors beyond this, right? So if you just go by that principle, you might think, well, maybe that's it. That's enough somehow to describe the unique structure of a 2-1 factor, but it turned out that was wildly off. There's a vast world of 2-1 factors here. Just for completeness, so the type 1 case, so we saw in Max's talk, that was yesterday, so type 1 groups. So type 1 groups, all representations, irreducible representations, give you B of H, essentially. These are type 1, the von Neumann algebra is B of H. Here you also have a semi-finite trace. You still have scales, but these scales are quantized. So you have atoms, quote unquote, in B of H, but you can't take sort of fractional values. That's the major leap in going from the type 2 to the type 1 to the type 2-1 case over here. Now you can have arbitrary real values between 0 and 1. Groups are very interesting because groups are somehow dual objects. So if you look at the group von Neumann algebra that's generated via the left regular representation, these are always type 2-1 objects. They're always type 2-1 objects. Yeah, if they're ICC. On the other hand, we can also look at a group somehow in its own terms, in terms of its own geometry. Of course, we've seen a lot of that this week as well. And from that point of view, you can witness type 3 behavior. So we've seen boundary actions, like for example, in Yair's talk this morning, we saw a boundary action, exactly this one here, the free group acting on its Gromov boundary, some quasi-invariant measure. There will not be an invariant measure, as we saw in the discussion this morning in Yair's talk and the connection to stationary states. This action here, it will generate a von Neumann algebra, but there's no trace. And all scales are equivalent. All projections are equivalent, as long as they're non-zero. So not only can you play at different scales, but everything, it's completely homogeneous. The structure looks the same everywhere. And that is actually not the case for type 2 1-factors. Question?
Question. Can you go back to the previous slide? If you look at the middle column, any of those algebras isomorphic to one another?
Oh, when are these isomorphic to one another? Yeah, I will get to that in a moment here. You can probably guess when the group, precisely when the group's amenable. In both cases. In both cases, even for the dynamics, yes.
Minimal, all three, right, would be the same as a.
Yeah, as long as if we stick in the world of amenable groups, all these are the same thing. These are all the same hyperfinite. Once we go beyond amenability, then all kinds of things can happen. We've already seen that this week. One can also transport this type 1, type 2, and type 3 terminology in the world of dynamics. So this can be interpreted here, well, type 2 actions, those are probability measure preserving transformations, which we've already discussed. Type 1 actions, the group acting on itself by translation, or if you have a fundamental domain which is measurable. If you have a measurable fundamental domain, that means you have a measurable set such that the group just maps it to disjoint copies of itself. So there's nothing interesting there. There's no interaction between the measure theory and the group. One is just replicating the structure of the group in the simplest possible way inside of the space. So there's nothing interesting there. You're just sent back to the analysis of the group itself. And the type 3 case and the type 2 case, this is where one has very interesting interaction between the group and the measure theory. I mean, you have a kind of measure theoretic pigeonhole principle, Poincare recurrence. This recurrence leads to all kinds of invariants like entropy that measure somehow the statistics of recurrence and all of these types of things. So one gets a rich, rich body of theory here. In the type 3 case, that's just there for completeness. So you can read there Nigel Higgs's quote. So yeah, if you chop this in half, somehow you get just 2 replicas of the original beast, which are equally as fearsome somehow. But if you cut things in half, if you cut a type 2-1 space or type 2 space in half, you very frequently get 2 copies of the original thing, but at a smaller scale. So you have made an improvement somehow. Yeah. But in the type 3 case, everything looks the same somehow. So, I mean, here's another illustration of the type 2, the dichotomy, if you want, between type 2 and type 1. So this goes back, I've framed this in terms of, so the German philosopher Hegel, when he was working the early 1800s, he made this infamous distinction between what he called bad infinity and good infinity. So the bad infinity is an aggregative or inductive infinity, right? Where you just keep adding something, right? And the idea that it's bad here is that you always have to go outside of what you have to somehow get further along in the sequence. And even worse, you don't even ever really get any closer to infinity by doing this. So in this sense, it's bad. The subdivision of infinity, I mean, you start from the whole thing. And you just you can sort of internally generate the infinity. Of course, in order to do this kind of internal generation of infinity, it's an inductive process. So you're applying the bad infinity at a higher order, but I think this is probably lost on Hegel. But one can interpret this nicely in terms of the dichotomy between 1 and 2, type 1 and type 2. And one can apply this principle. So here's amenability getting applied as this organizing principle. If you have a type 2 1-factor of a Neumann algebra, you can take its tensor product with B of H, all bounded operators on Hilbert space. And this corresponds to this aggregative infinity. So you've somehow amplified your algebra. You haven't somehow introduced, on the other side here, you tensor with a hyperfinite 2 1-factor, that allows you to subdivide your algebra. Whereas tensoring with B of H allows you to amplify your algebra. Of course, both of these operations are important for different purposes. But if one just wants to classify things to somehow unravel finer scale information, that's the one on the right that one really wants to achieve. And so in the best possible scenario, you'd like M tensor R here to be isomorphic to M itself. You'd like to be able to perform this inside of M, right? And this is the McDuff property, which we saw in Adriana's talk. And that will come back in a moment here. I just wanted to illustrate here. There's another illustration. So this is it's an American artist, Mike Kelly. This is a retrospective in Dusseldorf last year. I took this shot here, part of a larger project here. But I think this gives you some idea, some illustration somehow maybe of a matricial subdivision operation that is somehow illustrative of this hyperfinite 2-1 construction via matrix algebras subdivision. And this is another work by the same artist here. So So this idea of fundamental group of a von Neumann algebra, so this came up in, so I think Anna asked a question yesterday about the fundamental group, in Adriana's talk. So this fundamental group in a von Neumann algebra, I described this operation of cutting down by a projection. If you cut down by a projection of von Neumann algebra, you may obtain a von Neumann algebra which is different from the original one, may not be isomorphic. And this was a mystery for many years, and Kahn finally showed around 1980 that this can actually happen using property T. But now it's known to happen quite frequently now. So perhaps this is maybe an illustration of that. So you see there's some kind of homogeneity here, there's some kind of scaling behavior, but at certain scales you get what looks like maybe a change in the global structure. Something doesn't quite match up. Okay, so let's return now to the McDuff property. So the McDuff says, yes, if you tensor with R, if you allow for the subdivisibility using amenability in R, if you just get back to the original algebra M, that's somehow one of the best possible scenarios here. So you can do all kinds of things with this. And McDuff introduced this in her work in the late 60s. And she showed here it's actually equivalent to this other condition, which is much easier to verify in principle. All you need is a pair of sequences in the algebra that asymptotically commute with everything, but don't asymptotically commute with themselves. That's actually enough, surprisingly, to show that you have this kind of equality between the tensor product with R and M itself. So the hyperfinite 2-1 factor is itself McDuff. It absorbs itself tensorially. M tensor R then will also be McDuff, because if you tensor that with R, then R tensor R is just R itself, so you can collapse those two copies of R back into one. It turned out that many von Neumann algebras are not McDuff. So this goes back to this result that I mentioned of Murray von Neumann here. So the von Neumann algebra of a free group is not McDuff. So they did not have this terminology. They were speaking in terms of property gamma, which Jonathan mentioned. But the result shows in particular that L of Fn, the von Neumann algebra of the free group, is not McDuff. And to do this, they used the paradoxicality of free groups under conjugation. So not the paradoxicality that's related to amenability in terms of left translation, but under conjugation. Of course, this is still a type of amenability. One can talk about amenable actions. One can frame that in terms of this broader notion of amenability. So this is the point somehow where amenability entered. In fact, what did I say here? So in fact, that should be L of Fn. L of Fn is prime. It cannot be even factored as the tensor product of 2-1 factors. The result of Lim and Ge. And then Ozawa showed that for all non-elementary hyperbolic groups, in fact, this L of G is prime. You can't decompose it. He showed something actually much stronger, but that's one thing.
Yeah, I'm just curious about the historical motivation for this property, like being
McDuff.
Yeah. Why was it introduced in the first place?
Okay, so Murray von Neumann's original motivation was to find a factor that was different from R, from the hyperfinite one. And so they showed that this paradoxicality of the free group under conjugation, it shows that there cannot exist projections of trace a half that are approximately invariant under conjugation. That's the property gamma. And so von Neumann actually wrote about this in a later work. He said this is one of the very hardest problems that he worked on. And it took a long time to come up with this, even though, I mean, it's deceptively short. If you look in the paper, it's barely 2 pages. But it's maybe not so technically, I mean, in hindsight, it's not, I mean, you can understand it very easily nowadays, but it really did lead to, I mean, all of this development of Kahn and even C-star algebra classification theory, it all comes out of this. Even though at the time, I think they thought that this was an ad hoc argument. So later on, and so, I mean, it was the same question that prompted then McDuff to study this. Can we construct more 2-1 factors? And so she introduced this property and some variations on it. So quantified somehow the degree to which this may or may not hold. And she was able to show that there are uncountably many 2-1 factors. So that was a major step in the late 60s. So that was her motivation. But it turned out to be the key for the classification. So Kahn's classification a little bit later. And here is Kahn's, well, key step in Kahn's classification. So this is one of his major results here, that injectivity implies hyperfiniteness. So injectivity for a von Neumann algebra simply means that if it's an algebra of operators on a Hilbert space, that there's a norm one projection onto M. So it's an injective Banach space. That's all it means in a sense. So, I mean, this is very abstract. It doesn't seem like you could tease almost any structure out of this. This is the miracle that you can. And this is what Kahn showed, that this injectivity implies hyperfiniteness. And here's a summary of the argument. So it's a three-line proof here, but okay. Hidden behind this is a very deep, penetrating analysis of the automorphism group of injective factors. So what he showed us, so injectivity implies that you have a nice relation, a very tight relation to the structure of finite dimensional spaces in the Hilbert space via Hilbert-Schmidt operators. And using this finite dimensional approximation, which is not it's not enough to get you hyperfiniteness, but it's some leverage. He showed, first of all, that the automorphism group is so nicely behaved that, first of all, you can show that your factor is McDuff. That's the first isomorphism there. And secondly, that every automorphism and even automorphism of the tensor product of M with itself at the bottom is approximately inner. So it's approximately implemented by conjugation by some unitary. And then once you've proven those two things, then it's just a trick playing around with tensor products. So this is the trick right there. So if M is McDuff, it's the same thing as M tensor R. R is equivalent to its infinite tensor product with itself. That's something you can show. And so if you have a finite set inside of your M, and you represent M as M tensor, this infinite tensor product of R, then you can approximately realize your finite set into a finite head of this tensor product, of this infinite tensor product. And so you can rewrite M tensor R here in another way as M tensor R, so that your finite set is almost in M itself. Now the next step here, now suppose you could embed M into R. Okay, this is something you can't show directly. But if you could do that, then this M tensor M would embed into M tensor R. The flip automorphism approximately inner, so you can almost realize it by an inner automorphism. That unitary then will also exist in M tensor R. You apply it to the finite set, it will move it over to R. R is hyperfinite, so you can approximately contain this finite set in something finite dimensional. And then you apply your unitary conjugation back in the other direction, and you've approximately contained your finite set into something finite dimensional. This is local hyperfiniteness, but that's enough that you can show that this will imply that there's actually an inductive limit of these finite dimensional things. So you can't embed M into R. This is the source of the famous Kahn embedding problem. He showed that you can locally embed M into R. This is Kahn embeddability. That was sufficient to make the argument work, but that's philosophically what's going on. So McDuffness turned out to be crucial for this proof. So Popa and Hogger came up with other proofs of this, which this McDuffness is kind of suppressed, but it's somehow, it's still underlying in some sense. These kind of commutation relations are still underlying here. But this also turned out to be key, this kind of McDuffness viewpoint to developments, later developments in C-star algebra classification. So this is just repeating based on your question here. So if you're looking at cross products, G is amenable if and only if you get, for free ergodic actions, you get the hyperfinite 2-1 factor. For ICC-G, you get exactly R when G is amenable. The interesting thing here is that if you have a free ergodic action of an amenable group, you can directly prove hyperfiniteness from this tower construction. That's not, I don't think that's written down anywhere in the literature. It's a very nice exercise, but you can do this directly. To show that if a group is amenable, that you get R, this requires the full force of Kahn's theorem. There's no direct way of doing this. And if you attempt to do this, you'll appreciate the difference between looking at left translation and conjugation. Again, going back to my theme here, it's a major step in going from left translation, that expresses amenability in the group, to conjugation, to properties like McDuffness and this kind of thing in the operator algebra. And just to appreciate that, you can attempt to prove that directly. It's just not possible. So you really need the full power of Kahn's theorem. But it's interesting here that in dynamics, you can circumvent that. You can still apply Kahn's theorem if you want, but you can circumvent that. Because it's fairly easy to show that an amenable group will generate an injective factor. C-star algebras. So I mean, it's a similar story here. So C-star algebras are the topological analogs of von Neumann algebras. If you have an action on a compact space, you can form a cross product similarly from the left regular representation, satisfying the same kind of formalism here, the formula. You turn the action into a set of inner automorphisms. One can also do this for the group itself. One gets the unital C-star algebra, the reduced group C-star algebra. So I will come back to C-star algebras bit later. Not sure what's going to happen here. Okay, and the next slide. This slide is really the content of a whole course. So this is summarizing. A similar picture applies to a certain extent in the world of continuous actions on compact spaces. This is some development that I've been involved with myself, collaboration with many other people over the last 10, 20 years. Is try to transfer these ideas from the von Neumann ergodic situation to topological dynamics. And it's surprising how far you can go, but the Rocknell lemma it's not valid in generality for amenable groups. So one has to make some restriction. That's almost finiteness here, but it's surprising how far you can go. And what happens is that you have to find what happens in hindsight. It took some time to discover this. There's this analog of the hyperfinite 2-1 factor. That's the Jiangsu algebra, denoted Z over there. And all one can show from dynamics here is that one gets this Z stability. And then one has to impose the Z stability condition here in the classification theorem. There's a very nice classification theorem in this context under the assumption of Z stability. And so again, in the topological framework, this passes through this McDuffness phenomenon. You can't go directly from left invariance to good finite dimensional approximation. In the end, once you know your algebras are classifiable, there's a model theorem that tells you they have to be inductive limits. Not a matrix algebras, but something almost as good. So since I'm running out of time, I'll come back to that. Maybe I won't come back to that. But so here's the question. I guess my time is running out here. So I want to talk a little bit about a couple of recent projects very quickly here. Can fullerness, amenability, be used to study non-amenable objects? Well, there are many examples of that. Not so much in the type 2-1 context, I would say. So amenability as a principle is used frequently in the study of boundary actions, for example. So the Poisson boundary is always an amenable action in the suitable type 3 sense. But in the type 2-1 sense, this hasn't been explored too much. So one question here, when is L of gamma, the von Neumann algebra, if G is non-amenable, when can it won't be the hyperfinite 2-1 factor, but when is it McDuff? Well, we saw some examples in Adriana's talk of McDuff factors. I want to give you some more. Second questions here. If you look at actions of non-amenable groups, I'm specifically interested in free groups on compact spaces that admit invariant measures, that's at space MGX. They have invariant, at least one invariant probability measure, so they are type 2-1 in that sense. Can we say something about their cross products? These cross products will also be non-amenable in the operator algebraic sense. Right, so the first is joint work with Spiros, who's here, right there, yes. And the second is a recent project with my colleagues, Jamie Bell and Shirley Guffin, that provide some examples in these two cases here. So the first is topological full group. We've seen this appear a couple of times already this week here. So so if you have an action on the Cantor set, I'm calling the group now gamma because they're groups at two different levels. It gets a little bit confusing here. So gamma is another discrete group acting on the Cantor set. The topological full group is a group of homeomorphisms of X that are locally implemented by elements of gamma. So any homeomorphism set that admits a Clopin partition so that on these elements, it's an element from gamma itself that's implementing that. Yeah, so this is the full group. So Slava claimed it was impossible to change the awkward double bracket notation for this, but I've done it. Okay, so that's my notation there for the full group. Sorry, I don't have any pictures. Kind of ran out of steam in drawing pictures here. So one celebrated result here of Yushchenko and Monod is that for integer actions, if an integer action in the Cantor set is minimal, then this full group is amenable. And if you pass to the commutator subgroup, this gives you a simple group, and it's often finitely generated. So this gave you examples of simple finitely generated amenable groups. And in fact, so this is so Ellick and Monod then showed that for Z squared, this already breaks down. You have minimal actions that produce non-amenable full groups, and then Zirka showed that in fact you have a kind of Tietz alternative. As soon as your group is not virtually cyclic and amenable, then there's always free minimal actions that produce non-amenable full groups. And the idea is that you can embed free groups into these. That's how one does it. Okay, so this is a result with Spiros here that if we have a free minimal action with countably infinite amenable group on the Cantor set, so you look at the full group, its von Neumann algebra is McDuff. The proof here, interestingly, it doesn't require the full power of Fulner tilings. We don't need Fulner tilings or tower decompositions. It's just Fulnerness. And so what you do is, if this is your space X, we're using gamma. This is your Cantor set X. What you do is you look at towers, so Clopin sets with disjoint images under some Fulner set. Look at towers that somehow have this kind of shape. So they're the form F times D, where D is some subset of the group. F is some Fulner set. Thanks. And so in this direction, you apply elements in the group for which this is Fulner. The picture doesn't change much. In this direction, inside the full group, if you specify a tower like this, you actually get a full copy of the symmetric group over those towers. You just think about it a little bit, little exercise. So in this direction, you can collect together these copies of the symmetric group, in this case over 4 elements. You can bundle them together in this direction. And what you get, and then you can apply the symmetric group in this direction, you get a wreath product. So you get a model for Bernoulli action, but it's a finitary Bernoulli action. And then what happens in this direction, inside the von Neumann algebra, you get, well, you have to use some representation theory for symmetric groups. So you get a direct sum of matrix algebras. And inside of those matrix algebras, there you can build, supposing it's just a single matrix algebra, that's not correct. But if it were, then one can build, what we do here is we build 2 projections which are diagonal in this matrix algebra. And their trace is almost equal to 1, very nearly equal to 1. And we copy out those projections. And the product of those projections there, we want to arrange them to have trace approximately 1/2. And then what happens here is that these 2 projections, they are equivalent inside of this matrix algebra if they have the same trace. And one can implement that equivalence by some partial isometry in the matrix algebra. And it turns out that this partial isometry and its adjoint, these will asymptotically non-commute if one does this over larger and larger versions of this picture. So that's how one generates McDuffness. And what's interesting here, so to go back to this Halian division between the bad infinity of aggregative, inductive, right, constructions and subdivisive, this is kind of a technical transfer between that. Whenever you have a tower inside of a space here, that's a kind of aggregative, inductive, right? You can keep prolonging this tower here as long as you start shrinking the Clopin set. One gets a kind of inductive march towards infinity. But each tower generates a subdivision, a matricial subdivision inside of the von Neumann algebra. So it's really a technical transfer of this aggregative to a subdivisive infinity. So that's kind of what's going on there. So the other project here, just to wrap up here, so this is more on the C-star algebra side. We're looking at group actions of the free group on the Cantor sets. And what we're able to show here, actually using Fulner tiling, so this does use Fulnerness, asking for this McDuffness property in the C-star algebra world for actions of the free group, it's actually false. It's never true. So this Z stability that plays the role of McDuffness, it can never happen for actions of free groups. It would imply that the free group is interamenable. It has a conjugation invariant mean, and that's not true, going back to Murray and von Neumann. So we have to ask for something weaker, and what we were able to prove here is a property of stable rank 1. So this is a kind of dimensional invariant in C-star algebra theory. For commutative spaces, it really just boils down to the covering dimension up to a factor of 2. So it's kind of a complex version of covering dimension. So if you have a space of dimension 0 or 1, like the interval, continuous functions on that space will have stable rank 1. Because these are complex valued functions, right? Functions on the interval, the complex plane, these are just paths. In the complex plane, you can always perturb one to avoid 0. And stable rank 1 says exactly the invertibles are dense. That means perturbing such a path so that it doesn't hit 0. And a general principle in operator algebras is that the more non-commutative you get, the more you look like a zero-dimensional space. And this is a very important principle, and largely it is true, although there are counterexamples. And so the stable rank one, it ends up, it's one expression of this fact here. It does have some nice consequences. It was actually defined, it was defined by Riefel with the idea of applying this to stability problems in K-theory, which I won't get into, but there are applications. You can ask me afterwards. And the question is, when does this have stable rank one? So this Z stability, the C-star algebraic McDuffness, it does imply stable rank one if the algebra is finite, if it doesn't have any projections that can be compressed. Free group, the C-star algebra of a free group also has stable rank one, and this was proven by Dykema, Hagrup, and Roda using the rapid decay property. We heard about rapid decay, I guess, in Merdad's talk. This is really a type 3 phenomenon, I would say. So this is a type 3 proof. And I mean, we were partly inspired by this. We want to apply type 2-1 technique, so something completely different. Now, in the amenable case, some nice progress was made by Lee and Yu a few years ago. So this is, so actually Lutley and Alboyu initially proved this for actions of Z, then it was generalized by Lee and Yu. Actually, the result is more general than this. So they showed this for Z to the D actions, that the C-star algebra generated by that is always has stable rank one. And these algebras down here do not need to be Z stable. So this is a weaker property than this Z stability, this C-star algebra McDuffness. And stable rank one, even for simple C-star algebras, even for amenable ones, need not always hold. So there's these examples of village. And so we show that this happens somehow generically in nice spaces of actions on the Cantor set, actions of the free group on the Cantor set. Generically, you get this stable rank one. And the argument for doing this, so this is an argument that's often used. So it's an argument, a beautiful argument due to Roerdam. If you test some element in your algebra, and if you can express your algebra, non-invertible element, in good cases, you can perturb the element to a zero divisor, which means that, okay, if you can decompose your algebra, this matricial subdivision of your algebra here, so suppose this is a matrix algebra with entries in some smaller algebra, and you can diagonalize your element like this, and if it's a zero divisor, if you take a large enough matrix algebra so you can have zero up in one point there, in one place, then by applying a shift matrix, you can turn it into something upper diagonal, and therefore nilpotent. And then if you add something small scalar multiple of the identity to something nilpotent, it becomes invertible. Because nilpotent elements have zero spectrum, no? And so that's the trick. And so the idea is that, just to finish up here, we can have 30 seconds. Yeah, so we were able to show that this happens generically, the stable rank one, in two spaces of actions, ones that are weakly mixing, and other ones which are minimal and nuclear ergodic on each generator. Okay, so in some nice spaces of actions, we want to rule out periodic phenomena, odometers, because we actually know that these already have the property for other reasons. But we can show, especially this A star here, we can show this is a large space. We wanted to study this A star because we could show that this is actually a large space of actions. You don't know somehow in the descriptive set theoretic sense, in the bare category sense, how large this WA is. That's still an open question, but this A star contains a huge supply of actions. And so what we do here, so here's the property that we somehow extracted some structure in the proof of Lee and Yu and defined it in terms of a property here. So this is somehow something happening at the level of the space, which translates eventually into this matrix picture. So you can't diagonalize the block matrix, but you can almost diagonalize it. You have to almost diagonalize it in terms of blocks like this. So you get the appropriate number of zeros, and you can rotate by unitaries and then follow through with the trick. And underlying all of this is amenability. So we have to apply amenability. If you have a product trick, we're applying amenability in one of the generators of the free group. And this is very closely related to the notion of amenability by Greenleaf for actions on discrete sets in terms of the existence of Fulner sets. So we need to play off freeness and amenability. So it turns out that generically what happens for an action on the Cantor set, at some scale in the dynamics, the existence of Fulner sets and Fulner tilings of these sets, specifically towers, it somehow overrides the freeness. Right? So you have amenability at some scale inside of the space, and this is what allows you to produce these matrices in the end and apply this kind of diagonalization principle that is in some ways expressive of amenability. So our elements here are not, I mean, they're not normal, so they can't be diagonalized in the ordinary sense of linear algebra, but amenability is a substitute for that diagonalization principle. So it does allow you to block diagonalize in the sense in which you can still carry this out. Okay, my time's up. Sorry for going over a little bit, but maybe I'll stop there.
Thank you very much. So do you have any questions for David? Yes, as a
Yeah, do you expect this phenomenon of stable rank 1 to happen for all actions that emit an invariant trace or invariant measure? Say the free group.
Probably, it's hard to say. I mean, yeah, so you have the result for Z to the D that it always happens. It's always a little bit surprising. There's always this question. I mean, there's many things somehow we know for Z to the D actions now, and the question, maybe polynomial growth too. The question is whether that, say, polynomial growth is a genuine boundary to being able to extend these things, for example, to amenable groups. And maybe there's some feeling that maybe it is in certain cases. So, but here it's very hard to say. I don't know. One might conjecture, perhaps, that it's always true. There's something fundamental to the symmetry that one has in a group, along with its action, that is going to make this always true. But I don't know. I'm not willing to conjecture anything, but perhaps.
So I was curious about this result that for amenable group actions, the topological full groups, right? They have for them in algebras, MNiSW, right?
Yes.
That would be proved. And even though some of the groups are not amenable, as we know.
Yes.
Right. But do you have a sense that maybe those topological full groups are amenable in some topological sense, not as discrete groups, or is it possible? Because it looks like the argument you make it here, there is some kind of
completely independent of whether the full group is amenable or not, right? It's purely dependent on the amenability of the acting group.
of the acting group.
Yeah. Yes. So it has nothing to do. But that raises an interesting point. I mean, the question of when a topological full group is amenable, that's
Or maybe it's amenable in some topological, like a topological group with respect to some topology. I don't know.
yeah, I don't know. Yeah, but for the full group itself, I mean, determining when that's amenable, extremely hard question. We don't know. We can only basically, I mean, there's this basically the same construction, embedding free products of cyclic groups, in which they can then embed a free group. That's basically the only method we have for doing that. And this you can do over Z squared. As long as you have superlinear growth, you can do this. The point is that, just to describe that, if you have a full shift, like a full shift over the integers even, then the full group of that will contain a copy of F2. Because you can use the full shift here to translate somehow the classical independence into free independence. And so if you can embed a full shift, at least along some part of your group, maybe along an element of infinite order, then you can apply the same argument there. And that is compatible with minimality as long as that direction is somehow of density 0 in your group. So that will happen in Z squared, for example. Yeah, but other than that, I mean, we don't have a good idea of, well, maybe, for example, capturing amenability in some other sense. Yeah, I don't know. But okay, maybe to follow up on that question, maybe McDuffness. That's a good question. I mean, for actions of non-amenable groups, when do you get McDuff factors? They may actually be tied to the more recent project which I described here at the end. It may be tied to that. It's more generalized amenability phenomenon where the acting group is not necessarily amenable. So that could very well be the case. Yeah. Oh, that gives me some ideas. Thanks.
But I don't know if these topological objects are related, for example, with topological orbit equivalence. I don't know, something that you show that is true for CD action is not related with this result of Giordano, Matui, Putman-Skau, or not.
So that's a good, so yeah, that brings up the question of orbit equivalence, which I, yeah, didn't say anything about, somehow swept it under the rug. But so orbit equivalence, I would say in C-star algebra, so you mentioned Giordano, Putnam, and Skau. In the case of integer actions, the orbit equivalence viewpoint, of course, is crucial for saying something finer. I mean, I mentioned the classification theorem, that's in terms of ordered K theory and so on and traces. If you actually want to be able to compute the K theory and relate it to the properties of the dynamical system, that's where orbit equivalence comes in, yes. So that's a good point here. So if you're interested in that, in actually computing the invariant, seeing how that relates to the dynamics, there almost certainly you're going to have to bring in information about the orbit equivalence, the structure of the orbit somehow. But at this level, maybe that's somehow the point of my talk, at this level, just verifying the properties that will imply classification, you can bypass this question of order equivalence. Yeah. But of course, both are important. Yes.
So do you have any counterpart for this entropy? You know, on the left hand, on one side you have this world where you have group dynamics with left action, and then you have this algebra world with computation. On one side you have this nice, you know, classification like Bernoulli, this, and then the entropy. Do you have such stuff on the other kind of other side of?
I think some people have tried, well, like a Bernoulli, like an Ornstein classification. What one has, I mean, there are natural non-commutative examples of Bernoulli actions on the hyperfinite 2-1 factor. But one can take an infinite tensor product of matrices and just shift. But one can actually also allow for fractional base spaces if you want, somehow fractional weights. That can also be done. And one can classify, I mean, one can define entropy for amenable groups in the sense, I mean, that was developed in the 80s and 90s especially. In my thesis work, I actually worked on that, non-commutative entropy. As you might know, in the last 15 years, there's been a new theory of entropy developed, going back to work of Lewis Bowen for Sophic groups, a much, much wider class of groups. Very beautiful idea with many applications, but we don't know how to adapt that to non-commutative von Neumann algebras. That would be a very nice problem if anyone wants to work on that. So the extension of entropy theory from amenable groups to Sophic groups, there's something fundamentally different that happens when you go to the Sophic world. It can't be translated into operator algebras, apparently. I mean, I know when speaking to people, I've thought about this myself, it doesn't seem to be possible. And there's special reasons for being able to distinguish Bernoulli actions in the non-commutative world, because one has super rigidity results, non-commutative Bernoulli actions over property T groups, results of Popa and so on. One would want to know whether these things are different. It's actually of relevance. So hopefully that answers the question.
I don't see any further questions, so let's thank David again. Conference we start tomorrow at 9. And regarding
There's copy of that.
and regarding the colloquium, there will next week we will have Bashir Beka. We'll give a talk.